So this is a recording of the content that we give of a presentation at HotStorage2025 in Boston. And this is a research collaboration effort with Riverbeds and Ram Darajan from University of Oregon, and our advisor Ulrich Kremer and Sudarshan Cannon from Rutgers University. So let us begin the discussion uh, by discussing the growing threat of the wildfire incidents recently. According to NASA, the fire seasons are getting longer and getting more frequent due to the climate change and environmental stressors. And these wildfires are no longer isolated events. They are escalating in both scale and impact. And many of you may recall the large wildfire that struck Los Angeles area earlier this year. And destroying this wildfire destroying homes and displacing communities. And this kind of event of wildfire have used to be happening once in a generation, but it's now uh, these types of events gonna happen more frequently. And unfortunately, this is not the only pattern in America, because the Europe is also seeing the same pattern. For example, La Palma, Spain, wildfires have caused significant damage, and most recently, a massive wildfire in Greece burned over 100,000 acres of land and property. And these events underlining the urgency of strengthening our wildfire monitoring infrastructure. As wildfires become more intense and widespread, we must ask, how can we improve the robustness and the responsiveness of the systems we rely on to detect, analyze, and take action on these events in real time? So there are current solutions existing around to tackle this problem. And for example, firms from NASA and Aurora Tech providing a satellite-based wildfire detection. So these platforms are available for global coverage and have a large-scale situational awareness, but they can be limited in resolution and responsiveness. So complement these solutions, we have IQ Firewatch and Dryad. They provide a real-time wildfire monitoring solutions based on sensor and camera data. And one key example is Sage, which is a cyber infrastructure for edge computing. So the Sage project is a cyber infrastructure platform designed for real-time environmental monitoring using edge computing. So Sage nodes integrate a sensor arrays with on-site computing, enabling applications like data analytics and AI inference to run directly on the edge, close to the hazard. And here's take a look at the infrastructure of the Sage infrastructure. Here's in the remote and in the natural environments, this is the H node, which is deployed in the natural environments. They are equipped with cameras, smart sensors. So cameras on the top and sensors are the hub on the left side. And these devices continuously capture the environmental images and signals. And these signals are very vital for early fire detection and situational awareness. So these edge nodes are also equipped with computation, memory, and GPU. So these resources are provided by the integrated system on chips devices. So thanks to these resources, edge nodes usually do data inference or a wildfire detection on the real-time data collected from the sensors and the cameras. And frequently, the edge node communicate their data using multiple network options. It can be wireless, it can be Ethernet, it can be cellular. So this flexibility is essential in remote or infrastructure limited regions. And these data are going to be sent into the micro data centers, which are collected to solar powered, or they can be connected to the intermittent grid to achieve the sustainability and energy efficiency goals. So we call these micro data centers, we call them MicroDCs. These MicroDCs are intentionally designed with limited compute and memory capacity. And their role is to support near sensor processing and enabling low latency, energy efficient data analytics during emergency events. So how applications are deployed on this infrastructure? A popular option is containerization with Docker and Kubernetes. Containers offer portability, resource isolation, making it easier to run diverse workloads on the same node. This model is especially useful in MicroDCs. So on the infrastructure, we have to share applications together in the same node, and we have to support multiple frequently changing research deployments. However, containerization does not address deeper challenges like memory contention. When applications with different memory behaviors run together, interference can still occur, especially under tight memory budgets. So on MicroDCs, uh, they often run a combination of applications. For example, data ingestion, they have to ingest the data from the sensors, or data and logging storage applications using tools like RocksDB, an in-memory database with high performance with the persistence storage. And also data processing with machine learning framework, such as PyTorch models or OpenCV for computer vision applications. And these applications stress the memory in different ways. Data ingestion workloads use kernel and user space buffers to handle sensor streams. These buffers are for transferring data from device to the OS and from the OS to the user space applications. Logging and storage systems like RocksDB depend on the lookup tables, indexing data structures, and the file-back to page cache. Machine learning tasks such as YOLO inference allocate large tensors and move data between CPU and GPU. So these memory types are managed differently by the OS, but they compete for the same limited physical memory, leading to contention that is hard to predict or control. So these workloads do not run in isolation. These application memory demands fluctuate based on time of the day and sensor activity and incident response. Uh, a user strategy to run this application is that when in normal circumstances, uh, an optimal strategy for better energy consumption and for good carbon emission is running these applications together. So it's a application multi-tenancy. However, with this strategy of running applications, we also have a situation where wildfire events happen. Multiple applications also ramp up simultaneously to analyze incoming data and detect threats in real time. So this sudden spike in demand puts significant pressure on the memory, leading to memory contention across applications on the system. So this is the first major challenge of the MicroDCs, memory contention under real-world conditions. So an argument or a natural solution for this problem is just adding more memory. So there's no problem with it, right? However, in this context, we argue that this is not a viable option for MicroDCs. So unlike traditional data centers where infrastructure is accessible, the MicroDCs are deployed at the remote environment across the US, so often in remote locations with limited power and budget. Simply adding more memory is not practical. It increases cost and leads to higher energy consumption. These additional memory consumes unnecessary energy, even when memory is not intensive, due to their background power consumption. There is also environmental cost. Manufacturing memory contributes to embodied carbon, and these trade-offs conflict with the sustainability objectives of hazard monitoring infrastructure. So the next part is the motivation of the paper. So now, with the context of the MicroDCs, we understood that we should run applications in multi-tenancy, but adding more memory to the MicroDCs is not a viable option. However, this work wants to stress on the fact that the application multi-tenancy on a system has beneficial values, and therefore we might want to resolve the memory contention issue with a new approach. So let's see how multi-tenancy is helpful in these cases. So MicroDCs are designed for near sensor processing. So they sit at the remote locations close to the sensor and act as last layers of the computation in the stage. So when fire breaks out, the sensors offload the data and computation to nearby MicroDCs for real-time analytics. And in these moments, multiple applications must run together. Therefore, multi-tenancy is not a design option. It is a core requirement for how these systems operate. So we conducted a few experiments to understand the effects of running application in multi-tenancy. So here's experiment, and we choose out some representative applications to run. So the first application is YOLO, which is a machine learning app on the MicroDCs. It can do data processing and doing machine learning based computer vision. And YOLO can do real-time inference over wildfire data. And this YOLO use a heavy heap memory. And another application is RocksDB. This is representative for the data logging and storage type of application on the MicroDCs. RocksDB manages large volumes of sensor data and Wi-Fi imagery and even logs. And RocksDB heavily use page cache. And RocksDB is a popular database from Facebook from 2012. So the first experiment we run, we see the impact on the carbon emission. So on the x-axis represents decreasing system memory from left to right, and the y-axis shows the total carbon emissions. The lower is the better. And this is the results from the carbon emission on the y-axis is calculated from the model based on an ISCA paper. So we can see that across all memory sizes, shared multi-tenant execution consistently results in lower carbon emission comparing to isolation runs. This is because multi-tenancy improves hardware utilization, avoids wasted background power, and saves the system's operational and embodied carbon emissions. So here's the details of for the workloads of the experiment for the next experiment. So we understood the impact of the multi-tenancy and how it's beneficial for our context, but it still doesn't resolve the issue of memory contention. So that's why the next experiment is running YOLO and RocksDB together and see how the performance degrade. So for YOLO, we have a data set of 38,000 images, which is 7.7 gigabyte, and 8 processes do inference in parallel. For RocksDB, we have a data set of 20 million key value pairs with a value size of 4 kilobyte, and a total data set is 43 gigabyte. The RocksDB is going to do read 10 million random keys in database for each thread. So the experiment goals is to evaluate performance of the isolation execution and also evaluate the performance of shared multi-tenant execution. So here's the details of the machine setup. And we also did some experiments on this integrated system on chip. And this is our ongoing work on the multi-tenancy impact on both the local edge setup on real stage deployments. So the bottom right is the system on chips. If you see a very small circuit board, they have a GPU memory compute on that chip. And on the left side, on the top is the power measurement devices. And this is going to be our future work. So let's see the results on the impact of memory contention. On the left side, we have the RocksDB performance, which is on the x-axis is reducing system memory from left to right. On the y-axis is the performance throughput. The higher, the better. And here's the results. And on the right side, we have the performance of YOLO. On the x-axis is the system memory decreasing from left to right, and the y-axis is the total runtime for YOLO to do inference on the whole data set, which is the lower the better. And here's the results. So the result shows that on the right side, while YOLO performance does not get impacted or get minimally impacted when reducing the system memory. However, on the left side, the RocksDB performance was heavily impacted when running in shared environment or in shared resources with a YOLO application. This is because RocksDB heavily relying on the OS level page cache, which is deprioritized under memory pressure. We also conducted another experiment using containers with the same workloads and same configurations to see whether the current container solutions can resolve this memory contention issue. So here we have the same configuration, we have the same workload. We have the extra condition here is YOLO is containerized using C groups. They have an 8 GB memory limits, and this memory limit is for the best isolated performance. And we got this number by profiling YOLO application. And for RocksDB, we also containerize using C groups, and we assign the rest of the system memory to RocksDB. And this is the result for a container experiment. So we also see the same pattern here. On the right side, the YOLO performance is minimally impacted, when on the left side, RocksDB performance is still heavily decreased when running in a shared multi-tenancy style. So, what did we learn from the experiment? We detected the asymmetric performance degradation for applications using different memory patterns under memory contention. And we also learned that static partitioning, which is a usually strategy for containers to limit their own memory usage for the containers. So this static partitioning strategy fails to consider various memory types. This approach still relies on the OS level memory management and fails to consider the prioritization of page cache and heap memory. So what can we do to resolve this? We introduced PAMS, a multi-tenancy resource management framework. It has 3 features: unified treatment of memory types, application level triggers, and predictive resource allocation. So here's the blueprint of how PAMs work. So in the middle, we have the PAMs is the middle layer between the OS and the user applications. So PAMs will extend the OS level memory metrics for memory tracking, like C group level memory pressure or page fast statistics. This will give PAMs a better view of the system memory resources. So let's go to the first feature of PAMs. The first feature is having a unified memory classification model. So this model will dynamically promote different memory regions to be first-class citizens in the OS. And it dynamically promotes different types of memory. So by communicating with the OS that these memory regions should be prioritized, this will prevent critical tasks from getting into thrashing phases or getting killed. And PAMS achieves this by assigning priority labels for memory types, informing eviction and reclamation policies. And next feature is application level triggers. So PAMs will integrate hooks and telemetries at the application level. For example, classification and confidence in YOLO and ingestion rate in RocksDB. So these applications will communicate their app states with PAMs. So, and through these communications, PAMs can proactively respond to the app's dynamic memory demands, increasing CPU shares, migrating tasks to higher performance cores. And lastly, we present predictive resource allocation. And thanks to the application level triggers and system memory tracking, we want to propose the component. Um, we want to propose a component of like resource demand forecasting. So thanks to the information we gathered from the application level triggers and system memory tracking, we can have a time series data of when we can forecast when the applications are going to have a high demand in memory, and we want to proactively um, acting on those events. So this component we have balanced the performance metrics against the energy and carbon constraints. And lastly, we propose a lightweight machine learning model to adjust memory management knobs and in response to app and system states. In summary, we identifies challenges of multi-tenancy on MicroDCs for hazard monitoring. We also motivates the need of cross-layered approach to manage memory dynamically. And for future work, we want to explore whether PAMs can be implemented without significant changes to the OS. And thank you.